chat. Couple of things. The next homework won't be as hard as the first one. It's due Friday, and again, with COVID-19, get it in when you can get it in. So try to get it in by Friday, but if you get it in this weekend or next week, that's fine. What else? I revised the schedule. I posted a revised schedule up on Canvas, just due to making room for the Carbon Hackathon and, trying to be as flexible as possible this quarter. This week, we're going to look at buildings. The homework's going to focus on commercial lighting. And so I'll probably spend most of this lecture on commercial lighting and then get to heating if there's time. So have a look at the homework starting, today. And then Thursday, we'll have another homework study session. As the quarter progresses, I hope that the study sessions become more interactive, not just me going through it all. But expect something similar to last Thursday. Okay, I've gotten some indication from people that are overseas that they're having trouble accessing the Zoom cloud videos, even though I thought I figured out the password thing. So I'm moving probably to YouTube. I've already made one YouTube link for the study session. I didn't put it on Canvas yet, but I sent it to the people that couldn't access the video. So please let me know if you're still having trouble accessing Zoom, and we'll find a solution to work around. And by accessing Zoom, I mean the recorded videos. Because it is a lot of extra work for me to make the YouTube videos, so I don't want to do them if I don't have to. But if that's the only way for even one of you to access the Zoom videos, then let me know and I'll keep making YouTube videos. Sound good? All right, let's get into it. I have the chat here so I can pay attention. All right, so, and I'll say all that again at the end of the lecture just in case people are joining late. Okay, so we're gonna look at buildings today. Identifying and quantifying emission reduction strategies for buildings. Click over here. All right, so this is a little dated. This is from 2006, but the percentages haven't changed. And so this is the energy supply and use as sources of US CO2. The normal numbers that aren't in parentheses, that is that's CO2 emissions as a function of CO2 emissions, and then this parenthetical number is as a fraction of total greenhouse gas emissions. And so note they're a little lower for each sector: residential, commercial, industrial, transportation, because land use obviously contributes about 10%, and so it reduces those numbers. But raw CO2 as a function of energy supply for the US from these different sectors is as follows. You can see that buildings constitute 22 plus 18, that's like 40% of CO2 emissions. So it's a really important thing to focus on, and that's why it's the first of these couple of lectures looking at ways to reduce emissions from the different sectors. The other sectors are, of course, industrial. This is making stuff. It's interesting, Alcoa, the aluminum smelter, I read that it shut down in Ferndale, just north of here. I'm not exactly sure the reason why. I need to read more about it, but that will be a significant reduction of CO2 emissions, at least for Whatcom County. But I'm a little worried about it because it does obviously provide jobs, and it's not going to be easy to restart an aluminum smelter because I'm sure that like some of the crucibles where the aluminum's melted are now soiled with solid aluminum. Some of these big industrial processes require like steady operations, and as soon as you shut them down, it takes a lot of work to get them back up again. So we'll see what happens with Alcoa. I'll try to read more about it. That could be an interesting project for the class to look at. How much that might have cost them to shut down and how much CO2 is avoided.
When that happened, because we went there for the field trip class last year.
What'd you say, Andrew?
You know, did that happen? That must have happened just like very recently because we went there for the field
Yeah,
trip
I just saw it on
last
the
year.
Bellingham subreddit like 2 days ago.
Oh,
So who
well,
knows? It's Reddit, so maybe it's totally fake, but
yeah.
it's interesting. Yeah, I'll look more into that. Okay, so again, we're focusing on buildings because it's 40% of the emissions here. All right. So if we look at just the building data, and again, this is all from energy use, and then multiplying the energy that's used multiplied by the carbon intensity of that energy. So the energy from the electricity grid multiplied by the various regional carbon intensities for different grids, the carbon intensity of natural gas use multiplied by the amount of natural gas used. It's difficult to get to the actual emissions without first starting with how much energy was consumed and then multiplying that by a carbon intensity. So we can look at how much energy is used in buildings from these different surveys that have occurred over the last several decades. The most robust one, unfortunately, is this older 2006 date, but that's what's there. And so we can see that space heating is the dominant source of CO2 emissions. So just making areas warm. And so that's a lot, mainly from burning natural gas, right? And then lighting is another huge portion of the CO2 emissions. So that would be scope 2 emissions, right, from electricity use. Now, lighting isn't terribly big in residential applications, but it's big in commercial applications. And that's because stores are well lit. People want to move product, right? So they shine the lights big and bright, you know, and so lighting is a big component there, and they're just on all day long. Space cooling, this is important for larger commercial buildings here in Washington State and for all buildings in the southern states where you need AC, and water heating, and then a few other things. So this is similar to what you may have recalled from like Energy 101 or Energy 380 when we looked at personal energy use. Seems like a lot of students before they start Energy 101, they think like things that use a lot of energy might be like their computers, their TV, their stereo or whatever. But it turns out those things actually use quite a little bit of energy and therefore emit a small amount of CO2. Big things are, again, just lighting and keeping things cold or keeping things warm. So refrigeration and space cooling, that's keeping things warm. Water heating and space heating, or that's keeping things warm, and refrigeration and space cooling is keeping things cold. Cooking, keeping things warm. All right. Wet clean, that's a weird word. So I suppose that's opposed to dry cleaning, so doing laundry. I don't know why they didn't put laundry there. Kind of creeps me out. All right. So if you want more up-to-date information, you can look at the EIA.gov total energy consumption as a function of different sectors. So residential, you can get monthly data. Commercial, you can get monthly data, but it hasn't been converted to CO2. You'd have to multiply again by some carbon intensity, CO2 intensity for whatever fuels you assume go into those different applications. But they're all broken down nicely in PDFs. Now these PDFs end at the end of 2015. What happened in 2016? Any guesses?
The election?
Yeah. So the EIA got completely gutted by douchebags in power, and so now we're not collecting the data. Okay. Which of these are scope 1 and scope 2? I already said that one of them was scope 2, lighting. Which ones might be scope 1? You guys can type in text or talk out loud. Eloise, do you need something? Okay. Space heating, yes. So space heating is often just direct combustion of natural gas in a gas furnace. So that's... What about space cooling? Would that be scope 2 or scope 1? 2? Yep. I need to make this gallery view bigger. Wait, do we only have 6? No, we have a lot more than that. Okay, just Zoom issues. All right. Water heating, scope 1 or scope 2? Two. Yeah, mainly scope 2. Natural gas, historically, it's been cheaper than using electricity, so most people have natural gas water heating. Now with heat pumps, it's cheaper to use electricity, but obviously there's the upfront capital cost to buy a new water heater. Most all these other things are all going to be scope 2, right? You don't fill your computer up with gasoline. Refrigerators are usually. There was a natural gas refrigerator at one place I rented in the past. That's kind of weird. Cooking can be a lot of natural gas, especially in commercial applications. And for brewing.
This was lost and I found it.
Great. Okay, I got to get back to work, girls. Okay. So this next slide shows building energy use breakdowns for residential and commercial sectors. So again, what we're doing here when we're looking at these pie charts, we're trying to target areas of CO2 reduction. So obviously the biggest impact we can make is in lighting, space heating, space cooling, water heating. But it differs slightly between commercial and residential buildings. So here's residential breakout and here's commercial breakout. The biggest difference is this lighting. So percentage-wise, commercial has a lot more in lighting, and that's, again, they want the products to look good, they want the food to look good. Offices have lights on all day long when people are working. University, for example, has way too many lights on all over the place, and so these commercial buildings have a larger percentage of energy use and therefore CO2 emissions associated with lighting. And that's what the homework this week focuses on, commercial lighting for Pebble Beach Golf Course, and replacing some of the lighting to reduce CO2 emissions. Okay. And there's this interesting aside here. Lighting in commercial buildings, office spaces, stores, etc., adds to the cooling load, meaning that these lights aren't perfectly efficient, so they deposit heat into the buildings, and now we need to remove that heat, so the cooling load goes up, which increases CO2 emissions even further. And so by switching to more efficient lighting, you get a bonus. You get automatic CO2 reductions because you're using less energy to make the lights, but now you get further CO2 reductions because you don't have to cool the building as much. Let's check the chat. Nothing's going on. All right. End use analysis. What am I talking about here? Oh yeah, I was looking at scope 1 versus scope 2, but we already kind of went through this. So things that are electrical, powered by electricity, obviously are scope 2, meaning the emissions happen somewhere far away at a power plant. And so you'd have to get the emissions, you multiply the electricity use multiplied by the carbon intensity of that electricity. And if you want to be fancy, you can take into account like line losses and stuff like that. We talked about that, I think, lecture number 2. So electrical things are HVAC systems, cooling, ventilation, sometimes heat, lighting, refrigeration, other appliances, computers, TVs, electronics. And then for scope 1, it's whatever you're lighting on fire in the residence or the commercial building. So space heating, domestic, hot water heating, cooking, especially again in the commercial sectors. Most all restaurants use gas ranges because you can change the heat, instantaneously. You can turn the burner up or down. Induction stoves, induction hobs are just as fast as natural gas, and some restaurants are moving in that direction to reduce their carbon footprint. French Laundry, which is like Michelin star restaurant in Yountville down in Napa Valley, they pride themselves on being like zero carbon restaurant, and they have induction hobs and a wind turbine that powers them. Drying clothes can be natural gas or electricity. Yeah. Okay. So steps to reduce emissions. This is again just from the Bellingham Climate Action Task Force. Energy efficiency is the low-hanging fruit, the fastest one, the easiest one to do. So just provide the same service, cold beer, warm showers, number of lumens of light in a building, just with more efficient technology. Next, electrification. So try to get rid of the Scope 1 emissions. And you can often get deeper efficiency changes with electrification because you're going from high-grade electrical energy to whatever service you're providing rather than low-grade thermal energy trying to upgrade it to something. And then as things become more electrified, switch to renewable energy so the Scope 2 emissions go down. So this, again, same points we're going to hit all quarter long. So efficiency, use less, emit less. So most buildings within a particular class, office building, restaurant, house, are very similar to one another, and they have pretty generic energy loads. So this is opposed to like industrial buildings where they could have hugely different energy loads. And so we can kind of develop an algorithm or a checklist to begin to reduce emissions for buildings based on the class of building. So some of the generalizations we can make are building envelope. So this would be an efficiency approach. Make the shell as robust as possible. Insulate the building. Use insulating windows. Seal the cracks. Seal the seams. Then try to gain heat for free. So use building design, building structures to get passive energy from the sun, passive solar heating, and natural daylight when possible. And then once these two steps are done, this is the free energy, right? From not letting it leak out of the house and letting the infrared or the visible energy from the sun leak in. So then once those free things are done, then you start spending money, and you want to spend money on heating and cooling. So make your HVAC equipment as efficient as possible. This stands for heating, ventilation, and air conditioning. And then work on your lights, possibly with some smart controls. Then continuing to go down that pie chart for the smaller and smaller slices of pie, CO2 pie. Then look into efficient appliances, electronics, other plug loads. Commissioning means, choose appropriate buildings for their use. So a commercial building, try to maximize as much daylight as possible with skylights and windows. Now a house, you might not want it to be all windows because you want some privacy. So think about building design and commissioning. This is kind of a forward-thinking idea. And then finally, occupant behavior. People do stupid stuff in their buildings, right, that contribute to more energy use and more CO2 efficiency. And so some of this stuff can be learned through education, and when that's not available, then use automated controls and have things work to regulate energy use and therefore CO2 emissions. But don't go too crazy with these. One of the offices I was working in Palo Alto had like fully automated everything, but what was the problem? Yeah, so the temperature was measured in a different room than where the controls were, or where we were located, my lab was located. And so it'd say, oh, it's 68 degrees, like we can close the windows to conserve energy. And then the automated windows would close. But we were in this corner that was like in the direct like south facing sun, and so it'd be like super hot in the room, and it'd be, coastal California outside like 72, so it'd be like 80 in the room but 72 outside, so we'd want to open the windows but we couldn't because they're automated windows. And then this one girl, Jennifer, she's Scottish and she doesn't take no trash from a window, and so she cut the wire to the automated control and just now made it a manual window. So these are great, but let's not have the robots take over entirely, right? Maybe automated controls with some override that doesn't require cutting wires. All right, that's a little digression. Okay, so what's the ultimate goal? You want your load, the energy load, to be less than energy production. And that's what a zero energy building is. And there's a few around town that if we weren't practicing social distancing, we could have gone and visited, I suppose. So to get a zero energy building, you have to make more energy than you consume. And you could do that by just really overbuilding power production, but it's cheaper to try to reduce your energy load as much as possible. So focus on efficiency first. Once you get that as efficient as possible, then design a zero carbon energy source like solar panels or wind tailored to your building. So here's one of the first massive commercial size zero energy buildings was the Center for the Environmental Studies at Oberlin College in Ohio, USA. This is Zero Energy Environmental Studies building. Our environmental studies building at Western is not zero energy. I think it's one of the least environmentally friendly buildings on campus, mainly due to its age and design. A newer one is the National Renewable Energy Laboratory Research Support Facility in Golden, Colorado. This one really focused on design elements for passive heating during the bitterly cold Colorado winters. And so it captures a lot of energy from sunlight. And then it also had this like smart ducts and piping to take advantage of natural convection, so they don't need mechanical AC. Air flows through naturally through specially designed draft systems. Daylight lighting as much as possible, etc. And then the state of the art now is so-called living buildings, and there's a few in Germany, and I forget the right word for this. The ultimate version, whatever, is the Bullitt Center down in Seattle. And so this was built by Dennis Hayes, and the idea of this building is not only is it zero net energy, it's zero carbon, and these so-called living buildings ideally produce even more energy than they consume and sequester more carbon than they emit. So they're negative carbon, negative energy. And then they have these 7 petals. Some of them are physical, so like net positive water use, net positive energy use, materials that aren't toxic and that are sustainable and long lasting. And then others are more on the social end of things and aesthetics. So they have to be pretty. They have to support an equitable and just world and optimize well-being and health. So things like focusing on commuting and biking helps with that. Walking, beauty. I don't know. Generally good design aesthetics, windows, that sort of stuff. So if you have the opportunity, you should go visit this building. We do visit it every year every spring in 480, the Northwest Energy class. But again, social distancing will deny that this year. But maybe next year, if you're still around, you could check it out. Or you can just visit it whenever you want to. Yeah, here's just some more descriptions about it. Even the toilets, they turn the waste into dirt that they sell. It's pretty crazy. All right, so let's get into some of the analysis here. These slides, I'm still working on them, so the equations aren't as pretty as some of my other slides. So I apologize for that. But hopefully the math is still all there. So in general, we're still trying to produce these marginal abatement costs values. So we need to calculate energy of some project, energy use of some baseline without doing the project, and then the cost of those two differences, and then the carbon emissions. So the cost is directly associated with the energy use, and the carbon emissions is usually directly associated with the energy use. And so first thing you usually calculate with these sorts of analysis is how much energy is being used. And oftentimes this is applied across a city or across a state. And so we're not just focusing on one building, we're focusing on class of buildings. And so we have to take into account the number of buildings. And so N is population, or number of uses of something in a building, like space heating, for example. A is the activity level per unit population. And so that'd be like how many computers are in a computer lab if we were looking at making computer labs in Western more efficient, for example. How much lighting is needed, how many heating degree days, we'll get into that in a few slides, etc. And then I is how much energy is needed per unit activity. So that's the energy intensity. So if there's 20 computers and 20 computer labs, how much energy does each computer use? 200 watts, and then we'd have 200 watts times 20 computers times 20 computer labs, and we'd get the total energy use for computers across Western or something like that, or a few buildings at Western. So it's kind of like an ITAP equation, intensity, affluence, population, but this is population, activity, and intensity. It's just a general formula to think about. And it's probably something you could think of on your own, right? Energy services, again, for buildings, cooking, illumination, thermal comfort, refrigeration, etc. Yeah. Okay. If we look at it from a power company's point of view, and so if you get into power planning or utilities commissions or utilities economics, then you look at it from this point of view, and the unit of merit is this so-called unit energy consumption, and that's kind of like A times I. It's like the activity times the intensity. So you could take something like TVs, and the activity would be watching television, and the intensity would be how many watts the TV watt times time that TV is using to get the energy use. And then you calculate for each house how many TVs are there, and that would be the UEC, the unit energy consumption for televisions. And so again, energy use is population times activity times intensity, and population times activity can be the quantity of energy services, and the activity times the intensity can be the unit energy consumption. Again, this is all just kind of economics language, but if you come across these terms, I want you to be familiar with them. Unit energy consumption, the units of those are kilowatt hours per year per customer. So how many kilowatt hours does a TV use in a house over the course of a year? The reason why they have it described this way is then they can just multiply it by the population and get some numbers, and I'll show those in the next slide. So this is more for residents, this UEC, when you do activity times intensity. For commercial buildings, they're usually rated by the number of square feet, and so then you get this other term called the energy utilization index, and that's usually in kilowatt hours or BTUs per year, not per customer, but per square footage. And so then you can multiply it by the square footage of different office buildings, for example. Boring. So the thing to pay attention to is the amount of energy you actually save, is the service that you want, the activity generally doesn't change. In general, in cities, you want the population to go up. That means the economy is growing. And so the thing that you want to change is the efficiency of those different services. Okay, so let's look at some of these UEC, unit energy consumption. This is from a residential study down in California last decade. And so let's look at, for example, dryers. Unit energy consumption is 652 kilowatt hours per year per customer, and then you multiply that by the number of customers to get how much energy is used for drying clothes. Often you multiply it by the saturation number too. This says how many members of the population actually have a dryer. So there are 4 people that live in my house. I do not have 4 dryers. That'd be crazy. And so this saturation says that there's, for every 3 people, there's like 1 dryer. So here are some different numbers that you can use if you're studying, for example, Bellingham. You could probably apply these unit energy consumption, multiply that by these different saturation values, and then multiply it by the population of Bellingham, and you'd get a pretty good estimate on the amount of energy consumed for these different activities. And you can multiply that by the carbon intensity and get the CO2 intensity for these different activities in whatever city you're looking at. Obviously, some things are going to change, like heating and cooling is going to be a little different for Bellingham versus California. But this is a good start. No, I can't tie that right now. I'm sorry. Can't make bracelets right now. Give me an hour, okay? Sorry. All right. What was I doing? Not making bracelets. Okay, marginal abatement cost. So we've calculated how to determine how much energy is used in a building. You can measure it directly. If you want to make estimates, you can use these things like unit energy consumption values that have been tabulated. So again, we try to calculate these marginal abatement costs for everything we do in this class. Applying it directly to buildings, we really need to consider energy efficiency. And baseline gets a little confusing with when we're talking about energy efficiency, especially talking about things like insulating a building, right? You're making the building more efficient, but you're not replacing anything. You're blowing in insulation into your attic, for example. And so what is baseline? A good first stab at it is the baseline is clear if the projected future energy use can be taken as the same as the observed recent past energy use. And so you say, oh, I needed this much heat in my house. I can say that's baseline, and then I can measure the heat afterwards that is necessary, and you get a change, so that you can do that project minus baseline. And then you can begin to index over several different houses and get some general idea of what before and after insulation may look like. It's a little easier when you're replacing a technology, so like a gas water heater with a heat pump water heater, or one light bulb with another, because then you can directly measure what baseline and project energy use is and energy costs are. But even that might change, right? Especially for something like a commercial building. You eventually want, more people going through your restaurant, and so the energy use will continue to grow, and carbon emissions will grow even though your efficiency has gone up because you're just, making more beer or whatever. So let's look at some. This is all just the same thing, but written more cleanly. Okay. So let's look at some of these different efficiency measures for residential. Again, the biggest carbon emissions are heating and cooling. And so the first thing you do is building envelope. This is more important in smaller buildings like houses because the surface area to volume ratio is bigger. You have to, more of the air inside the building is exposed to the outside, right? And so things like insulation, better windows, avoid infiltration of air. These are really important things for smaller buildings. And then passive solar, to try to get heat for free from window orientation and thermal mass. So make it out of materials that are have a higher heat capacity, so they don't cool as quickly and they don't heat as quickly. In Energy 101, I show a picture of Milan and Houston, which have identical climates, but they have very different cooling loads in the summer, and that's because Milan's made out of marble, which has a super high heat capacity, and Houston's made out of steel. Okay. Efficient air conditioning, heating, water heating, blah, 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 blah. So by electrifying air conditioning and heating, you can get efficiencies above 100%, and that's because you don't need to generate that cold, or you don't need to generate that heat. You move it from outside to inside or inside to outside. And so you use electricity to run a pump that moves the heat rather than using electricity to evaporate a refrigerant for cooling or run a coil for heat. So heat pumps are certainly the way to go with all of this. And then next to heat pumps is probably combustion of natural gas if you're in a dirtier power grid. And then if you're in a clean power grid, that would be the only reason to use resistive heating directly, but that still you'd be much better off with a heat pump. Okay, so all the different components of the greenhouse gas calculation. So when you're looking at these different pieces that go into heating a house, so passive solar, insulation, heat pumps, etc. All these different things are a way to reduce greenhouse gas emissions. So increase passive solar. Hey, Elle, can you please not play the piano right now? Thank you. So all these different methods of generating heat in your building are a way to reduce carbon emissions. For buildings that are already built, you need to just insulate and then change the heating appliances. Okay. So how do we measure the CO2 emissions? We have to look at something called heating degree days, which we'll see in the next slide. And then we have to look at how much heat the building needs or how much cooling it needs, and then what is providing that heat or cooling. This is messy math, but it's actually, when you think about what's going on, it's pretty simple. How much heat do you need over the course of the year? How do you get that heat? So the CO2 emissions is how much energy you need over the course of the year multiplied by the carbon intensity of that fuel that generated that heat. This 10 to the 9 just converts from mega BTUs, million BTUs to BTUs, and kilograms of CO2 to metric tons of CO2. The actual units aren't that important here. You're already good at keeping track of that. You're in a 400 level class. What's important is knowing that to get the CO2 emissions, it's how much energy you need multiplied by the carbon intensity of that fuel. How much heating energy you need for a building will depend on the heating load, so how much is needed over the course of the year, multiplied by 1 minus the percent of heat you might get from solar. So this would be due to better windows or better building orientation. And then the total heating load is divided by the efficiency of your heating appliance. And so if it's a natural gas furnace, then the efficiency is like 80%. So that's 0.8 on the denominator. So the amount of heating energy is going to be greater than the heating load, right? Because 20% of that heating energy went up the smokestack. If you have a heat pump with a coefficient of performance or an efficiency of like 300%, well then your heating energy is only going to be about 1/3 of the heating load because you got 200% of that heating energy for free by moving it from the outside or the ground into your building.
Can this bowl go in the microwave?
Yeah, do you know how to use the microwave?
Yes.
Okay, go for it.
Bye.
Just do it for like 30 seconds, okay? 3-0 start.
Okay.
My God. Okay. They're getting loose as the quarter goes on, I guess. I used to have them militant, but not anymore. Okay, so to get the heating load, we need to think about something called heating loss rate. And if you've taken building classes from Froy or Imran or Joel, feel free to take over the lecture because they know way more about this than I do, and you probably know more about this than I do at this point. But in general, you calculate the heating loss rate for a building, and so this is dependent on your insulation and your ceiling and the building materials, and then you multiply that by how many heating degree days are required. Now, heating degree days depend on location. Let's get into that. So here are heating degree days. It is the difference in outside temperature and inside temperature. And in general, we want the inside of buildings to be 68 degrees Fahrenheit. And so if it's, what is it outside right now? It's 55 degrees. And so that means that we have this, oh my God. Okay, I gotta check on something real quick. Okay. Let's see here. Heating degree day. So it's 55 outside, 68 in house. So that means if it was 55 all day long, then the heating, this house I'm in right now would have a heating degree day for today of 13, right? So 13 degree difference for one day. That'd be 13 heating degree days. And so you take how many days of the year are below 68 degrees multiplied by that delta of temperature, add it all up, sum over every single day and every single delta T, and then you get the heating degree days. And so that's why we have these huge numbers, right, for different locations. So let's look at some of the craziest ones. 11,500 heating degree days. Now those are located in, what is that, Wyoming. And so these are probably high elevations that are really windy and bitterly cold all winter long. So you have these big delta T's from outside to inside, from outside to 68F, and then several days of the year where that's necessary. We can look at heating degree days in Florida, and it's 500. We can look at the heating degree days in Hawaii, and most heating degree day values in Hawaii are less than 100. The only locations where you have heating degree days are at the top of the volcanoes where you're, 10,000 feet, and so it's cold up there. Makes sense? And so the thermal load that's necessary for different buildings, the heating load, will be 24 hours a day multiplied by the heat loss rate, how much heat your house is leaking per hour, multiplied by the heating degree days. And that's why that value is useful. And so colder locations have higher heating loads. Intuitive sense, right? You live in a colder place, you need more heat in your house. Okay. So the way to reduce carbon emissions for heating is move to a warmer place. Barring that, insulate your house so you're not leaking as much BTUs. And then think about occupancy too. Maybe you don't need to heat your house all day long. Maybe you're gone during the day, and so you can let your house go down to 60 degrees. You don't need to keep it at 68 degrees Fahrenheit all day long. And that's where something like a Nest thermostat becomes useful. It thinks about occupancy. All right. Along the lines of heating load as a function of temperature, this chart shows gas use versus temperature, outside temperature, and you can see that if it's below freezing, there needs to be now this is therms per a season, so for like winter. So if the average temperature is 30, then a house might need 175 therms over the course of that winter. If the average temperature is 68, then it needs nothing at all, maybe just a little bit for cooking. There's always some load, so like I'm slowly transitioning my house away from natural gas use, but even in the summer I burn some natural gas, and that's just to cook with, right? I don't have a fancy induction stove yet. Similar to heating degree days, there's cooling degree days. And so it's the delta from 65 degrees, unfortunately. People like to cool their house to 65 rather than 68. And so if a day has a mean temperature of 80 degrees Fahrenheit, that would equal 15 cooling degree days. Again, it's the delta in temperature multiplied by the number of days. So one day and a 15 delta, 15 times 1 is 15. Okay, and if the next day was 83, then the delta T is 18. And so for those 2 days, the cooling degree days is 33, 18 plus 15. So here's cooling degree days. Cooling degree days, we have 0 here in Bellingham. If you have an AC running in your house in Bellingham, it means either live in the attic and that's not your fault, or you don't know how to open a window. So you shouldn't need an AC here. As we go further south, or even to the tropics, then obviously ACs become more important. And even in the Great Plains, you need an AC, even though they're fairly north, and that's just due to continentality, right? They're colder in the winter and hotter in the summer because they're not regulated by these huge heat capacity sinks known as the oceans. Okay, so to limit heat load losses, and then therefore your energy use, and then therefore your CO2 emissions, you should insulate your house, and it's recommended by the Department of Energy that you insulate your house to these different R values depending on your location. So here in Bellingham, we're in region number 4 or zone number 4. So this is coastal temperate and not that cold at all relative to many places in the country. And so here we need attic insulation at R38 to R60 and floor insulation at R25 to R30. So what's R? It's a measure of temperature flux per watt of energy. So it's delta T over watts, delta T per meter squared. So you have like a square meter of attic or a square meter of wall. And delta T is the difference between outside and inside, and this flux is the watt per meter squared of heat flux through the barrier. So let's unpack that a little bit. What would our value of 1 be? That would be 1 watt. If there's 1 watt of heat flux, then the temperature difference between outside and inside is just 1 degree Kelvin. So why is bigger numbers better? R60 would say you could have a temperature difference between inside and outside of 60 degrees. So that would be like, 8 degrees Fahrenheit, the absolute coldest it ever gets in Bellingham. And you'd still only have 1 watt of heat flowing through your wall or through your attic per meter squared. And so if you have 100 square meters of wall or attic, then that means with R60, even if it's 8 degrees outside, then you're only losing 100 joules per second, 100 watts. And so that would mean that you need a space heater of 100 watts to maintain temperature inside your house. Human being is 100 watts, and so you wouldn't even need a space heater at all. Just by metabolizing food, you would be able to warm your house if you had R60 insulation. And that's, of course, assuming no leaks whatsoever, which would be crazy. And so having R38 to R60 insulation in Bellingham means that your house will very slowly lose heat as long as it's well sealed. And you don't need as thick of insulation or as high R value in warmer locations, obviously. Okay, why is this important? We're trying to calculate CO2 emissions and cost. More insulation costs more, but it avoids heat loss, which lowers CO2 emissions. Just building up our toolkit here. Okay, so the take home from all of this is to actually calculate a MAC, you'd have to go on a building per building basis because each buildings have different insulation needs, have different shapes, different square footages, different windows. And so we have to rely on averages if you want to get a good estimate. To get the true MAC, you'd have to actually install it and calculate the difference in energy use over the course of a year or two. And so if we were to average this over several houses, which is what the Oak Ridge National Laboratory did with the Recovery Act. So after the Great Recession, there was a stimulus that went into making things more efficient, buildings more efficient, cars more efficient, things like that. And so they studied how much money was spent and how much energy was saved through these energy efficiency practices across the nation, after 2008. And so the Oak Ridge National Recovery Act study showed that on average there's 12% energy savings through insulation. or $223 per year on average for the average house. And the average house, the upfront cost was around $3,000. And so, payback time over a little over 10 years. But from this, you could annualize it, calculate a marginal abatement cost. The 12% energy savings could be applied to operational costs. It could also be applied to carbon emissions, right? You could look at what energy was heating that home, and then, the baseline would be that original energy use, and the project would be that original energy use multiplied by 0.88, right? 1 minus 12%. So for the sake of this class, this is basically all we'll do. We'll just use this estimate here, unless you have specific information on a house or a restaurant or a building that you want to look at. Okay, next to insulation, the other important things are air sealing. So this is removing all the cracks around windows and doors and just throughout the house in general, where pipes or cable enters or exits the house. Insulation is the most important in the walls and the ceiling. And then having better storm windows and storm doors. You can get a lot of information about all this stuff from National Renewable Energy Laboratory or ENRG.gov. Let's not talk about cooling unless we have time, because that's not something terribly appropriate for up here in the north. And I don't really want to go into like some of these bizarre metrics they use. They have like strange efficiencies like BTUs per watt, and I'm like, yeah, you're mixing units. Okay, so let's go to lighting, because that's what we need for the homework. And then we can go back to this. Buildings. Energy efficiency, refrigerators. Residential water heaters. We did this on the MAC lecture 4. I think I did do heat pumps. I'll go to that heat pump calculation after we do lighting. That's a calculation Patrick and I just did last week. Okay. All right, lighting. 18% of all building use. It's about 12% for residential buildings and 25% for commercial buildings. But in general, it's about 18%. So it's another huge piece of the pie, and that's why it's something that we can target to reduce emissions. Blah. Energy efficiency measures in lighting, appliance, electronics, and other products achieve the same service for less energy. So this is just saying, energy efficiency is great because you get the same thing. You just use less energy doing it. And also there's this positive feedback loop I mentioned earlier, that when our plug loads use less energy for the same service, there's less waste heat generated within our buildings, and so we don't need as much AC. And in the homework, you'll look at the reduction of AC load for Pebble Beach Golf Course as we swap their lights for more efficient models. Okay, so taking our energy equation, again, energy savings would be the delta from baseline minus project for the number of units we're using, population multiplied by the activity multiplied by the energy intensity of that activity. For lights, it'd be how many customers do you have. Activity would be number of lamps per house, and multiplied by how many hours per year they're on. So that's the activity of the lights. And then the intensity would be the how much light we're producing divided by the efficiency of that lamp. That would give you wattages. We'll unpack this in the next couple slides. So the change in intensity, again, this is complicated words because it's generalized, but use your head is actually pretty easy. The change in intensity is just like the baseline efficiency of whatever lamp you have minus the efficiency of the project lamp, the more efficient one. Same with TVs, computers. You can measure the wattage needed to provide a service, and then subtract from that the project. So you could replacing. You guys are all too young to even remember the old-fashioned TVs. Maybe you're babies, but they used to be like huge, and they were terribly inefficient, and they'd use hundreds of watts. And now TVs just use like a few tens of watts. So swapping out an old-fashioned TV for a modern TV would create like hundreds of watts in savings. Okay, we showed this maybe even on the first day, but this is the quick dumb way to look at swapping lighting efficiency. And so again, it's project minus baseline for the costs over CO2 from baseline minus project. And so for this particular one, the capital costs, and again, I didn't annualize, well, I annualized this just by dividing by the number of years. So it's like I had a discount rate of 0%. I had no time value of money. But the LED bulb lasts 5 years. It costs $2. So $2 divided by 5 is 40 cents. The old-fashioned bulb only costs $1, but it only lasts a year. So per year, it costs $1. So that's capital costs. Looking at operational costs, you take the price per unit energy, and so that's 10 cents per kilowatt hour here in Puget Sound energy grid, multiplied by the activity, that's A, so 1,000 hours per year, and then multiplied by the intensity. The intensity for the project, the LED lamp, is 10 watts. The intensity for the baseline is 60 watts. Similarly, for the carbon emissions, we take the carbon intensity of the fuel. Fuel is kilowatt hours of electricity. It's 0.5 kilograms per kilowatt hour of electricity. Do a little conversion to metric tons from kilograms. Multiplied by A, the activity is 1,000 hours per year. Multiplied by I, the intensity. And now it's baseline minus project, so 60 watts minus 10 watts. And we can see that the marginal abatement cost for swapping out old-fashioned light bulbs for new ones is about negative $221 a year. So that's the simple way, but I wanted to go through that example again so we're all comfortable with what we're going to be doing for the homework on Thursday. But please have a look at that earlier. So in the homework, we'll be swapping out big fluorescent tubes for more efficient ones, or even for LEDs. And when you're going into commercial space, it's not on a per lamp basis or a per bulb basis. It's on a per square footage basis, because that's how they think, how architects think, right? We need to light up this cafeteria. How many lumens do we need per square foot? How many lumens do we get per light? That's how many lights we need. Okay. Here I was just saying, if you want to get the real CO2, then you'd have to consider line losses, stuff we talked about on lecture number 2. Line losses, heat rates, all that stuff. But again, just use eGrid, right? Use EPA's eGrid, or just use the value for PSE, which is 500 grams per kilowatt hour. But if you want to do it for real, then you have to consider all these different things. But eGrid does that for us. For energy efficiency measures, source energy doesn't change, blah, blah, blah. We know that. That's why we kept the energy intensity here the same. And yeah, okay. Commercial lighting. So for commercial lighting, the population multiplied by activity multiplied by intensity. Now the population is, I mean, it's weird to call this population, but it's how many square feet we're trying to light, multiplied by the energy unit intensity, and so that's kilowatt hours per year per square foot. So for commercial lighting, N equals, usually it could even be millions of square footage of floor area. Annual usage would be hours per year. So if you're a clothing store, you're going to be open, 10 hours a day maybe. So 10 times 365 maybe minus 52 if you're not open Sunday, or Monday if you're Paris. Multiplied by lumens per square foot. Lumen is a very weird unit. It's like quasi-physical, but biased for humans. So it's the amount of luminous flux. So we know radiative flux, right? That's just how many watts of radiation you're being hit with over the entire spectrum of light. So radio waves, X-rays, UV, visible, etc. Luminous flux is just the flux of radiation within the visible spectrum. So what our eyes can see. It also falls off with radius squared, right? Just like any light. So if you are twice as far from a light, then it appears 4 times less bright. And that's because the light is, growing as a sphere. And so lumens are usually defined as 1 lux, which is 1 lumen a foot away. And a lux is related to a foot candle, whatever. Don't worry about it. Just know that light is measured in lumens, and it's a funky unit, but it's something that we've all agreed upon, and so it's what we use. Okay, and so lighting efficiency is also often described in lumens per watt. So you remember, efficiency is just get over pay, what you get over what you pay. And so more efficient lights, you get more lumens per watt. That makes sense. You get more light energy within the visible spectrum per watt put in. Less of that wattage is turned into heat. It's turned into light. Commercial lighting, there's a few other things to pay attention to. Let me get my pointer back up here. So that efficiency, that lumens per watt, depends on the efficacy or the efficiency of the light itself, of the light bulb, and often it's fluorescent. And fluorescent lights require something called ballast. And so what is fluorescence? You're tricking a noble gas into kicking an electron to a higher valence band, and then it falls back down and releases a photon. That's what fluorescence is. You're running a current through a gas, causing the electrons to elevate in their energy level, and then when they fall back down, they got kicked up by electricity, and when they fall back down, they release photons. And so that ballast, kind of like a boat ballast, it's keeping things afloat. And what is it keeping afloat? It's keeping that electricity level just right at the quantum level to kick electrons up, such that they continuously release photons in a stable way. And so it's not very detectable to us unless you're an OCD person that can't stand fluorescent lights, and you can still detect the 60 hertz flicker, right, of photons falling back down. You definitely can see bad ballast in fluorescent lights, and that's when the fluorescent lights flicker, or they have those like pulsating waves of fluorescence going through them. They give you eye strains and seizures and stuff like that. So ballast, to maintain that flow, isn't perfectly efficient either. So you have to multiply it by 1 minus the percent loss due to maintaining that ballast, and that's usually given for a particular fluorescent bulb, and then multiplied by the fixture efficiency. And so that's the power source that's being modulated to maintain that ballast. So it's kind of boring, kind of complicated, but all these different things go into the total efficiency of the light. So how many lumens do you get out per watt? You put in a watt, some is lost in the light bulb, some is lost in the ballast, and some is lost in the power conditioning source. Not as complicated as it sounds. And these values are usually all given for different types of lights. How much CO2 you emit depends on how much electricity you need over the course of the year, multiplied by the carbon intensity of that electricity. How much you need depends on your population, how many square footage of lighting you need, how many hours that light is on per year, and how many lumens per square feet you need. So the lumens per square foot, that's going to depend on what you're doing, right? So if it's an office space, you'll need like comfortable, like mid-level light so that you don't get eye strain, but it's enough that you don't fall asleep. A restaurant, you don't need nearly as much lighting, right? You want to you want it to be more romantic, and you don't want to see the table too far, 20 feet away from you, and so the lighting's much lower in like a restaurant setting. Movie theater will have just super minimal lighting, right? Just for finding the exit rows or whatever. And so this will depend on the actual purpose of the commercial building. And then again, carbon intensity of electricity. And then to get the delta in CO2 from baseline to project, you go baseline, one over the efficiency of the baseline for whatever light you had, minus 1 over the efficiency for the project. And in a sense, that's what we did back here, right? This was the efficiency here to provide the same amount of light. All right, this was just a little further description on all that. Okay. Similar to residential lighting and residential building heating, each component of that lighting, energy, load calculation, population, intensity, carbon intensity, blah, 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 efficiency, these are all different ways we can reduce greenhouse gas emissions. You can pick different options and think about the cost effectiveness of these different reduction options. So for commercial lighting, you can reduce the number of hours per year the lights are on. Back in the 80s, for some reason, and I was too little to remember, but back in the 80s, like cities across the world, and especially America, kept their lights on all their skyscrapers, their office buildings, all night long, as just like, a flex. They were trying to say, like, look how awesome our city looks at night. There's still, like, Hsinchu does that. Like, you can see all the crazy LEDs going on there. And so over the course of the 2000s, all those buildings decided collectively to reduce their carbon footprint to turn off those lights during those hours. So we can reduce carbon emissions by lowering the number of hours per day or per year the lights are on. We can, instead of having the entire floor lit up, you can have occupancy controls that automatically turn the lights on and off depending on the presence of someone. And so, a lot of bathrooms around campus, the lights are off until you open the door to the bathroom and then the light turns on. So you don't need to light up a bathroom if nobody's in there. And then another thing, you can look at the efficiency or the efficacy of the light of the lamp. Because it's not a true efficiency, it's not dimensionless, it's lumens per watt. They call it efficacy. That's where that name comes from. You can have better fixtures, better ballast for fluorescent lamps. That could reduce. And then finally, again, with more efficient lighting, you lower the cooling load because you're not depositing as much waste heat into your environment. You're just depositing more lumens per watt, not as many BTUs per watt. Okay, so let's look really briefly at fluorescent lamps. They're still often the most cost-effective option for commercial buildings. LEDs are getting cheaper and cheaper. LEDs are great for residential buildings because you can just swap out the bulbs. But to have the big tube lights that are found in commercial buildings, those LEDs are still pretty expensive. Right, so fluorescent lamps are sized by tube diameter and length. The number T5, T8, T12 for these different tubes, this is like some American nonsense I don't get. It's how many 1/8 inches in diameter it is. So T5 would be 5/8 inches in diameter. T8 would be an inch, right? 8 times 1/8 is 1. And then, T12 is like a 1.5 inch diameter tube. As they've gotten smaller, they're putting out nearly the same amount of light, but requiring far less electricity. They're becoming more efficient. And their ballast has gotten better. So the older ones run on electromagnetic induction, and the newer ones run on solid state electronic components, and so they're much more efficient. So it's swapping out, for example, T12s with T5s. It's a wise thing. So you have better ballast and more efficient light. So this combined with T5's bulb's ability to provide more light lumens than other bulbs means long-term cost savings on your commercial and residential projects, etc. The best thing to do is LEDs, but they have a longer payback time. So most buildings today, they have T12 bulbs, and you could slowly swap them out, go directly to T5 here, or you could go to LEDs. And this just shows some of the efficacy, so lumens per watt for these different ones. So this T5 has 80 lumens per watt versus 60 lumens per watt, and has better ballast. So instead of 20% loss in the ballast, you only have 5% loss in the ballast. And so the total efficiency is 67% for T5 versus 42% for T12. And so for the sake of your calculations, you just look at this final efficiency. In the homework, I force you to mess around a little bit with square footage and lumens and that sort of thing. Keep track of your units, you'll be fine. Different nation states and states here in the United States are forcing new commercial buildings and building retrofits to become more and more efficient with their lighting. So maximum lighting power densities, watts per square footage, is going down over time for these different commercial buildings. Okay, so when you're thinking, if you're in a consultant position and you're trying to reduce costs and carbon emissions for an office building, these are the steps you need to go through to complete the project to the best of your abilities. So the thing you want to think about is what's actually done in the building. What's the visual quality of the task? Is it a movie theater? Is it an architecture studio where you need really good lighting because you're on a table all day long, etc. Then once the task is understood, think about the geometry of the space, how light is bouncing off walls, paint, surfaces, floors, ceilings. In general, you want light bouncing off upper regions of the wall and the ceilings down onto your work surface. You don't want light bouncing off the floor because that causes glare and discomfort. So think about painting things appropriately, having darker floors, lighter ceilings, that sort of thing, to reduce glare and increase the lighting quantity and quality. These things have all been measured and studied to like insane degrees. There's a lot of money in this. I think it's I don't know, I don't have the patience for it, but if you do, then this is a way to make a lot of money in architecture. It's like lighting efficacy, lighting efficiency, lighting quality. Then once you have the space figured out, think about trying to get the light for free. So harvest and distribute natural daylight. You can do that with controls, different. In my bedroom, it's south facing, so it gets too warm in the summer. And so I have like a little blind on the outside of my house that goes down to limit the amount of light that goes into that bedroom during the day, because I'm not there, I don't need it lit, and so I keep it dark. And then at night I open up that exterior blind to let in moonlight and starlight and city light and let heat leave the bedroom. So think about controls and harvesting or not harvesting natural daylight. And then once you've done those first 5 steps, think about where the light should be placed and how much light you need. And then think about activity levels of those lights. So how often do you need them? How often do you need to replace them? Training is for commercial buildings, so teach people to turn the lights off when they leave at night, that sort of thing. All right, there's plenty of daylight. We've known this for the last 2,000 years of building design and civilization, and we've seen instances all over the world in all cultures where we take advantage of daylight. Unfortunately, post-industrial revolution, Discovery of caffeine. We now stay up at all hours of the day. We need. They don't know what came first, like lighting or caffeine. There's interesting like studies on this. But unfortunately now we burn more light during the day. We have lights on more during the day than we do at night. And that's because we've designed our buildings to be able to be occupied all hours of the day. And we've designed them to be, larger. So there's many portions of the building that don't have access to external lighting. And so we have more light in the day. You can see that in so many lecture halls around campus where there's like no windows at all. And so designing buildings for daylight is an old technique, and now it's becoming a new technique all over again.
Dada,
Yeah.
can we have bath times in the bath?
Can you have bath toys in the bath?
No, bath.
Bath crayons in the bath. Yeah, if you can find some bath crayons.
Well, we already found.
Cool. You can have a bath tonight. Jeez Louise. Okay, so design buildings for daylight. There's some awesome train stations in Paris and New York City, Grand Central Station, where it's all about natural daylight. And so you don't need lights if you can just use daylight. And so people really geek out on this. Again, architects, so you can measure the fraction of daylight across an office space versus the fraction of artificial light, and you can design, the amount of luminaries or lighting you need over the course of a space by integrating the total lumens as a function of distance from natural daylight. So these cubicles don't need any lights on, and so the lights are off. By the time you're here, you need a little bit of light, so these are at 50% intensity, and then the newer hires that have the crummier cubes are way over here, and they need nearly all artificial light. So artificial light is up to 100% here, and daylight decreases over time. So thinking about space, thinking about painting, floors, ceilings, reflectance, all these things are a way to have great quality light that's conducive to whatever the building is designed for, while minimizing the amount of electricity we actually need to use to power that lighting. Here's a state-of-the-art library. This is in Fossil Ridge High School in Colorado, and it's nearly 100% daylight. No artificial lighting needed. Here's a textile factory in North Carolina that was redone for combination of daylight, natural daylight, and artificial light. Daylight for the general space, and then artificial light specifically for different textile looms and machines. Here's a store. Maybe this is what Dark Hagen looked like before I got to Bellingham, and this is now a store with natural lighting. And it just looks better, right? This is going to sell more product in this place because it's prettier. Okay, and then finally, smart controls for lighting are useful, and also for heating. Okay, let's see here. Have about 10 minutes left. I'll go into the the heat pump calculation another time, because I just wanted to really hit lighting for the homework because that's what we're focusing on, and then maybe next week we can go to heating. I think we'll do a little transportation next week too. That's what I'll do. I'll pull up the revised schedule, see what that's looking like now. So, sorry, let me find it. Share screen. Where is it? Let's do this whole screen. Okay, so here's this. Home. So I posted a revised schedule to take into account for the Carbon Hackathon. So we're here right now doing buildings. If you want to learn a lot more about heat pumps for both water and domestic heating, read Imran's newest paper that he published just a few months ago. It's excellent. If you want to learn more about lighting, I've also posted this Lou et al. Paper. Thursday, we'll work on the homework. Next week, we'll do transportation, and still haven't quite figured out that. It may be a combination of like buses and electric vehicles. We already looked at ton kilometers for the very first homework, but maybe we'll just have a few slides on shipping. And then utilities, so reducing emissions from where the electricity comes from. Again, that's like the third leg of the stool, going from coal and natural gas towards renewables. And then mid-May, we'll do land use, which I know nothing about and haven't even started those lectures, so we'll see what happens with that. And then we'll get into projects for the last 2 weeks. The projects we were going to do for 3 weeks, now we're only doing it for 2 weeks, so it's going to be even less serious. I don't think I'll have a final report that you'll need to generate. You'll just need to generate a presentation. Last couple announcements. I lost the chat. Homework due May 5th. I have it due Friday. I can make it due May 5th. Let's do that.
Wait, what? May 5th is so long.
That way it gives you Thursday to work on it, and then you can work on it all weekend. So let me switch that around. Other announcements, if you weren't here in the very beginning, apparently people overseas are having trouble getting access to the Zoom cloud meetings, even though I've gotten rid of the passwords and all that. Please let me know if that's still the case. Obviously, I don't know how that's going to happen, because if you can't get the recording and it's nighttime where you are right now, then you're not going to be here now. So maybe I'll make an announcement on Canvas regarding that. At any rate, I've started to generate YouTube videos for the people that request them. It's a pain, so I'd rather not do it. So if you can get Zoom figured out, go for it. If you absolutely can't get it figured out, then I'll continue to generate YouTube videos. What was I doing? Oh yeah, changing this homework due date to the 5th. Other questions, concerns, comments? All right, there are a lot of slides and a lot of discussion about so many different things today with respect to buildings, but it's all, the math should start to make sense for you all. It's kind of the same math over and over again. How much energy are you using? How much does that energy cost? How much carbon is emitted by using that energy? And then we can reduce the amount of carbon emissions by simply using less energy or using energy with less carbon. It's the same general format. Maybe I'll start posting like a summary page of equations. Oh, I can work on that. And I'm not sick. I don't know why I have a little irritation. I think it's allergies. So don't worry about me. Maybe I've just been drinking coffee all day and not any water. Doesn't look like there's anything else going on in the chat. I'll hang out for another 2 minutes, see if anything happens. Otherwise, have a look at the homework, and we'll hit it on Thursday.
Thanks, Charlie.
Yeah. I guess somebody just said goodbye. All right, everybody's peacing out. All right, I'm out of here too then. Have a good day.